Hi and welcome to Geeks for Geeks. Today we would be discussing this problem. In this problem, for each element, you need to count the number of elements on the right hand side. Okay, so let us just quickly take an example. So suppose we have 12, 1, 2, 3, 0, 11 and 4. Okay, so for 12, what are the number of elements that are less than 12 and have the count? Okay, so we need to return the count. So the count initially is 0. We have an element on the right hand side. This would become 1. We have 2 less than 12. So this would become 2. We have 3 less than 12. This would become 3. We have 0 less than 12. This would become 4. We have 11 less than 12. This would become 5. We have 4 less than 12. This would become 6. So for the first element, the value is 6. So for 1, so I will just quickly remove this. Okay, now let us take the scenario when it is 1. For 1, initially it is 0. Then we have 2 which is greater than 1, so we won't count it. 3 greater than 1, 0 less than 1, so it would be 1. Then it is 11 which is greater than 1, 4 which is greater than 1. So yes, the value is 1 at the end. Okay, so now we move forward to the next element, that is 2. So for the 2, we have initial count as 0. 3 is greater than that. 0 is less than 2. So we would increment the count. Then we have 11, which is greater than 2. And then we have 4, which is also greater than 2. Okay, fair enough. So the count is 1 again. Then let us do for 3. Initially, the count is 0. We have 0, which is less than 3. So we would have the count as 1. 11 greater than 3. 4 greater than 3. So the final count would be 1 itself. So for 0, the initial count is 0. Then we have 11, which is greater than 0. Okay. And then which is 4, which is greater than 0. So the final count is 0. Then we come across 11. For 11, there is only one element to consider, that is 4. Okay, which is less than 11. So the count is 1 and the value gets to 1. Then for 4, there is no elements on the right hand side. So we can say that the value is 0 itself. Okay, this is how the value is coming in. Okay, so now how can we solve this problem? The first brute force approach then we can think of is the first brute force approach that we can think of is by using two loops. Okay, so suppose we have same array we would copy here. So what we can do is we can stand at this index and then we can iterate over there. Okay, we can do this for the right hand side. Then we would stand over here and we would iterate over here. We can do this. And then we would stand here and we would iterate over here. So we would be iterating over this. Suppose this index is I and we would be using one more, that is j. So for each element, we would be iterating on the numbers. So in the worst scenario, so if we see for the first element, we would be iterating for n minus 1 element. For the second element, we would be iterating on n minus 2 element. And for the third element, we would be iterating n minus 3. What is n? Just for your confirmation, n is the size of the array given. So we can say that for one iteration, we are doing an operation. So for n iteration, we would be doing n square operation. That is why the time complexity of this approach is n square. As we are just using loops and we are initializing just the variables and we are not using any auxiliary data structure, the space complexity of this approach is big O of 1. Okay. Now let us move forward with the usage of policy-based data structure. So policy-based data structure can be thought of or can be visualized as the hidden one in the C++ STL. Okay, so in C++ STL, we have a kind of hidden gem that is known as ordered set. Okay, we have something known as ordered set. In ordered set, what we can do is, so the basic set that we have and the ordered set, what is the difference between them? Okay, so let us see the difference. So if we talk about only the set, in set, we can't use lower bound or upper bound like we do it in array or vector or other containers. But in ordered set, we can do. kind of like, not lower bound or upper bound, but we can use find by order. What is find by order? So if you use find by order, then it would tell us the number of elements less than. Okay, it would tell us the number of elements that is less than. So we would use this feature to have our result. Now, how we would use this feature or how this ordered set is coming into picture. So I would talk about this. Suppose we have the same one. Suppose we have the same array. So what we can do is we can start going from the last element. Okay, we can start going from the last element. Why? Because for the first element there is no element initialized. So 4 would be standing in here. Okay, then we initialize the value 11. So for 4 the value is 0 because the ordered set would tell us that there are 0 elements that are less than 4. So now 4 would be inserted in the ordered set. Then we have 11. 11 would be stored here. So as this is an ordered set, so 11 would be stored here. Okay, so 11, the number of elements less than that is only 1, so the count would tell me 1. See, we won't, so what we need is, we don't want the elements on the left hand side to be considered. So if we don't want the elements on the left hand side to be considered, we can start considering elements from the right hand side, so that the left hand side elements won't come into picture until they are needed. So we would use the same thing. Now let us move forward and let us see the implementation. Then we would talk about some bonus tips that we can do. Okay, so before moving forward, there is that ordered set, as the set performs, would store unique elements. So to handle this thing into picture, what we would do is we would start inserting elements in pairs. We would start inserting elements in pairs that would make them seem unique. How they would make seem unique? Like suppose I have an array of 1 and 1. So the only thing that would differentiate them is the indexing part, because we are given an array. So what we can do is we can insert 1 0 and 1 1. And even if they are the same element, we can use it as a multi-set kind of thing, where the duplicates would also be considered. And if we do the find by order, the first element would be considered by default. So we won't have an issue that yes, the second element of the pair is serving as the uniqueness that we need to convert it to a multi-set. Okay, so now there is one more bonus tip that we can use. So now suppose we want that, okay, Siddharth, but I want the find by order thing, that to search the element that are greater than that. Okay, what would be the scenario? Okay, suppose a question, this is not the question, this is kind of out of the syllabus, but suppose we want that. So in that, what you can do is you can start inserting elements. Okay, when inserting, so to have this find by order, the opposite of it. So to have the opposite of it, what we can do is just when inserting, just multiply the value with -1. And after taking out, suppose we want the element current element. So if you want that element, after taking out, again multiply it with -1. And this would convert your find by order. Find by order would search the number of elements less than that. This would tell us the number of elements greater than that. Okay, so you can use the same thing to convert the default priority queue to the min heap to max heap or max heap to min heap. We can do that. Okay, so let us move forward with the implementation using policy based data structure. So what we would do is we would define it. Okay, we would hash define it so that you can use it kind of template. Okay, so we would say ordered, then tree, and then pair of int and int. Instead of int, we used pair of int and int. Okay, the only difference is that. Okay, so this line, this ordered set, is copied from the article that is mentioned in the description of the video. So we would directly use this, and in place of int, we have just replaced it with pair of int and int. Okay, so now we would start the implementation. Okay, so we would first initialize the vector int of answer of size n itself, and then we would say ordered set, and we would name it as OS. Okay, and then we would start moving forward, and we would start iterating from the back. Int I is equals to n minus 1, I is greater than equal to 0, and I minus minus. Okay, and then to initialize the answer, first we would start considering it, then we would insert the current element. Okay, and we can do it either ways because we would be finding the elements less than that. So order of key, we would use this thing, and then we would have the values, and then as the second element is not considered, we would simply search it with 1. Okay, and then when in the case of inserting, we would use the indexing to have the uniqueness, that is the I itself. Okay, and then after that we would just return the answer. Now let us just compile and run and see. Okay, we need to change the name of the array. Okay, yeah, and yes, it is coming correct for the sample test case. Now let us submit and see if we are able to get an AC or not. And yes, we are able to get an AC. Now let's see something. Yeah, so let's talk about the space complexity and the time complexity. See, the space complexity of this approach is, in the worst scenario, we would be inserting all the elements. So it is big O of n. So for finding the order of key, this is taking log n, and for insertion also this is log n, and we are iterating over all the elements. So for one operation we are doing 2 log n. Okay, for an operation we would be doing n 2 log n. Okay, so constants are ignored, that is n log n is the time complexity. Okay, so we are done till this point. Now let us discuss the third approach. The third approach is by using the segment trees. So the understanding and the implementation of segment tree is a prerequisite here. So consider learning segment tree from the video as well as the article link mentioned in the description. Whatever is your preference, but my preference would be that you see the video and then move forward to the article. Okay, so the third approach is by using segment trees. So as the understanding of segment tree and its implementation is a prerequisite here, so consider learning segment trees from the description itself, links given, the video link and the article link both are given. So use it according to your preference. So now, as you know the understanding of segment tree and the implementation of it, let us see how segment tree can be used to solve this problem. So we have the nodes as the leaf elements. So now let us see how we would build up the segment tree. So the idea to build up the segment tree is that we would store the sorted array till a point, and suppose we want the elements less than that or greater than that, what we would do is we would simply use a lower bound that would tell me the number of elements less than that. Okay, so suppose we have 12 and 1. So initially every single element is a sorted element, we know that. So it is fine. So now 12 and 1. So when they both would merge, we would have 1 and 12. Then 2 and 3, it would remain the same. And then we have 0 and 11, it would remain the same. And then we have a single element, that is 4. Now let us go up, and then we would have this merge part. So merge of merge short, the merge part of merge short is the same here. So we would have 1, we would pick the first element, then we would take this first element of second one, and then we have 3, and then we have 12 itself, and then here we have 0, and then 4, and then 11 itself. Now we would stop that. Okay, we would stack all the elements and have in the sorted order. So first one is 0. Okay, we have that. Next we have 1. Okay, then we have 2, and then we have 3. Okay, then we have 4, and then we have 11, and then we have 12. Okay, so let us see how this would work. Okay, so suppose this is for the index 0 0, this is for the index 1 1, this is for the index 2 2, this is for the index 3 3, this is for the index 4 4, this is for the index 5 5, this is for the index 6 6. Okay, so now this one would be for 0 till the value 1. This one would be for 0 till the value 3. Why? Because they both would merge. So this one would be till 4 to 5. This one would be for 6 to 6. Okay. Now we would merge this also. So 0 till 3. So the easiest way to have this is take the first element this and the last element this. So we would have 0 and 3. We would have 4 and we would have 6 itself. And then here we would have the first one, that is 0, and then 6 itself. Now suppose let us do some query. Okay, let us do some query. Like suppose we want the number of elements less than, let's say, 1. Okay, there is only one element, so it is easy to do that. So for index 1, let us do for index 1. So what we would do is we would give the range 2 till n minus 1. Okay, that is index plus 1. So I plus 1, because we need to see the number of elements. Okay, number of elements less than that on the right hand side. So the left hand side, so the number of elements on the right hand side. So on the right hand side, what would be the indexing? It would be I plus 1 till the very end. So it is 1, 1 plus 1, that is 2, till the very end, that is 6. Okay, so let us do that. So 2 till the value 6. So 0 till the value 6. Okay, it is having that range. Okay, but it is not inside it. So we won't do the binary search here. Okay, so 0 till the value 3. Okay, so 0 is here and 3 is here, and the query is 2 and 6. So it lies some part of it. So we would go down. If some part of it lies inside it, we would go down. If the whole part lies inside it, we would take the consideration. Okay, so then we would go down. Okay, then we have 2 and 6, and 2 and 3 is within our range. So we would do a simple lower bound over it. So how many elements are there less than 1? So we would simply do a lower bound, that is the element there. So it would point to the very first index. So it is pointing to the very first index. That means there is no other element. So we would simply do I minus minus, and that would tell me the layer element. So how am I doing that? I would tell you that also. Suppose we have 1, 2, 3, 4, 5, 6, and I want to know number of elements less than in a sorted. Suppose we are given a sorted array. So we are maintaining the sorted array. How we are finding? So we want number of elements less than 4. Okay, so indexing is 0 1 2 3 4 and 5. So what we would do is we would simply do a lower bound. So lower bound, if the element is present, it would tell us the first occurrence of it. If it is not present, it would occur to the next greater element. So we want the less than that. So whatever element it is pointing us, it is on our favor. So it would point to this one. So what we would do is we would have the indexing, that is 3. So we would have the indexing 3. So number of elements less than that. Now suppose I want, let us do a query for 1 also. Then we would understand. So if it is pointing to the very first index, that means there is no elements that is present. So we would simply have that. Okay, 0. So whatever it is on our favor. So if we do a lower bound over 2 3, it would point to the very first element. The index is 0, so 0 would be added at this point. Okay, so 2 3 is done. As 2 3 is lying inside the range and it is processed, so we won't be going down. Okay, then we have 4 and 5. 4 and 5 is also inside the range, so we would do a lower bound. Okay, so lower bound, if the occurrence is not present, it would point to the next greater element. That means it would point to 11. So indexing of 11 is 0 and 1. That means 1 would get added to it. Okay. Then we have the 6. So 6 is in the range. So we would again do a lower bound. And the indexing of 4 is 0. That means 0 would add. So at the end, for the 1, the value becomes 1 itself. Okay. Now let us do a dry run for the next index, that is 12. Okay, then you would get a best grasp of it. So for the indexing 12, so the index is 0. So we would search for the range 0 plus 1, that is 1, till n minus 1, that is 6. So now we would start searching for it. So we came across 0 and 6. It is having the range, but 0 and 6 is not inside the range. So we would go down. Okay, we would go down 0 and 3. No, it is having the range, but part of it, not the whole of it. So 2 and 3. 2 and 3 is in the range. So we would do a lower bound of it. So if we do a lower bound of it, it would point to the last index, that is outside the element. Okay. So if it would be end position. So this is known as the begin position. This is known as the end position. So it would point to this index and we would have that. So the value that would get added is, this would 0, 1, 2. This would be 0, 1, 2. So 2 value would get added. Okay. So now this index 2 and 3 is done. So we won't be going down. So now let's go to 0 and 1. 0 and 1 is having that, but a part of that. So what we would do is, we would go down. So 1. Yes, we would do a lower bound over it and it would point to end position, that is 0 plus 1. So we would simply add that. We would add that also. So this is processed. This is processed. Now let us use the red color. So now the next one is 4 and 5, which is within the range. So yes, we can do a lower bound over that. So if we do a lower bound over that, it would point to this index. That is, the occurrence is not present. So it will point to the next index, that is 0, 1, 2. So 2 would get added again. Now 6 is within the range. Is 1 to 6. See, 1 and 6. So 6 lies at this point. Okay. So we can again do a lower bound and it would point to the end part, that is index 1. So again 1 would get added. That is why the value would come out to be 6. So now what we would do is, in the leaf node, when L is equals to R, we would assign the value. Okay. Now when we would go up, we would have the sorted form over it. We would just use the merge function of the merge sort. And then whenever we are doing a query, we would simply do an update is not required of segment tree. Now let us move to the implementation part. So let us change the name so that we don't have the same issue like we had last time, changing the name. So now we know from here that at each node, we need to store the array or a vector. Since array is a dynamic sized one, so it is easier to move forward with the array part. So what we would do is, we would simply have vector of int, and then we would name it as t. Okay. And then we would have vector of int of b. Why are we having this? We are having this because at each one, by building and then having the query, we need to pass the array again and again. So in this vector v, we would be copying the elements of a to v so that we don't need to pass the array a again and again. Okay. Then what we would do is, we would have the build part of it. Okay. So we would have void. So we would have it, yeah, void. As the build part won't return anything, so what we would do is, we would have the first index and then we have L and then we have the R part of it. Okay. So if I told you that the last leaf node, when L is equals to R, it would have that element only. Okay. So what we can say is, T of ID is equals to V of that particular L itself. Okay, we have that, and then we would simply close it, and from there we would return it. This would act as the base condition. Now when we are coming down, that means L is not equal to R. So what we would do is we would have int mid is equals to L plus R divided by 2 itself. We would have that. Then we would build the left subtree and the right subtree. So build of ID multiplied by 2, that is the left one, with L and then mid. Okay. And then we would have build of ID multiplied by 2 plus 1 and then mid plus 1 to R itself. Now this is just for the implementation thing. So what are we doing is we are having 1 and then we are having 2 and then we are having 3. So every time the root node would be, if root node is equals to ID, then the left part would be ID multiplied by 2 and ID multiplied by 2 plus 1. So I will just show you an example how this is working. So suppose this is 1, this is 2, this is 3, okay? And then this is 4, this is 5, this is 6, and this is 7, this is 8, this is 9, this is 10, this is 11, this is 12, that is 13, this is 14, and this is 15. So it's absolutely a personal preference how your implementation would be, but I'm just talking about my implementation and it seems so much simple that yes, the root node is 1, the left one would be nothing but multiplied by 2. So even if you see 5 multiplied by 2 is 10 and then 6 multiplied by 2 is 12. So everywhere 7 multiplied by 2 is 14, 3 multiplied by 2 is 6, and the right part of it would be multiplied by 2 plus 1. Okay, that is why this is, suppose we want to access the left part of it, we are going to ID multiplied by 2. If we are going to right part of it, it is ID multiplied by 2 plus 1 itself. Okay, fair enough. So we have built out the segment tree. And then what we would do is, suppose the left and the right part is built. So we would have T of ID is equals to combine, okay, T of ID multiplied by 2 and T of ID multiplied by 2 plus 1. We would combine the left and the right. Okay, so we need to write a combine which would return us, because at each node we are storing a vector of int itself. So what are we doing is we would write a combine function also. So we would have vector of int and then combine and then vector of int of a, and we would pass this by reference so that we won't have any issues of PLE, because pass by reference is faster than pass by value. So we would have B, and arrays are passed by reference by default, and we would first have the size. Int n is equals to a dot size. Okay, and then m is equals to b dot size itself. Okay, we are having this. Then we would have a vector of int of res of n plus m, because we know that the resultant value would have the elements of both. So the value would be n plus m. Then we would have I is equals to 0 for A, then j is equals to 0 for B, and then k is equals to 0 for the value res itself. Okay, then while I is less than n and j is less than m, this is a part of the merge function of the merge sort. Okay, so we would start taking elements of a of I is less than equal to b of j. If the first one is smaller, we would return the first one. Okay, that is res of k, and then a of I, and then we need to move forward both, like k would move forward also and I would also move forward. So we would simply do it here itself instead of explicitly doing it. And else what we would do is res of k plus plus, now you know it, so we would be directly doing it in b of j plus plus itself. Okay, then if some elements are remaining in the first a, so while I is less than n, what we would do is we would simply have res of k plus plus is equals to a of I plus plus. And then if some elements are remaining in the B, let's check that also. So J is less than M because the size for J is equals to M, and rest of K plus plus is equals to B of J plus plus. We have this. So we would return the resultant one, return the resultant value. So we are having the combine and the build part of it. Now we just need to write the query part of it. Okay. And writing the query part is a simple, but an understanding is required, which is already done. Okay. So we would have the query, we would have the ID part, we would have L, and we would have R, and we would have LQ, and we would have RQ. What does this mean? That left query and the right query. So this is just I plus 1 to n minus 1. And this L and R would be the same, that is from 0 till the value n minus 1, and ID would be the value 1. Okay, we would be doing one indexing. So if it is outside the boundary, okay, that is RQ. So I would just explain you what this is all about. So suppose we have the indexing as L and R. So suppose the current value we are considering, suppose this is LQ and this is RQ. Suppose L and R lies here. That means R is less than LQ, the first one, or it is lying here. Then it is of no use to us. That is the first condition when L is greater than RQ and R is less than LQ. So we would have this. So when RQ is less than L, or either of them, we would simply ignore that, or LQ is greater than R. Okay, so LQ is greater than R, that is this one, LQ is greater than R, or RQ is less than L, the second one. Okay, so in this scenario it won't contribute anything, so the value would be 0 itself. Okay, so now we would be going down, that if the current value is in the range, that is it is inside it. Okay, so LQ, if L is greater than LQ, that means it is nothing but sort of like this, that is L and R, either it would be equal or it would be inside it. Okay, so we would simply quickly have this also. So L is greater than LQ and R is less than equal to RQ. Okay, so now we would use this auto IT is equals to, we would start doing the lower bound of it, that is lower bound of T of ID dot begin. Okay, and then we would T dot ID dot end, we would specify the range and then the value. Okay, so we would need the value also here to search, because we would be provided with a value at the end. This would be int val. Okay, we would use this value thing, and then if it is referring to the very first index, that if it is equals to T of ID dot begin, that means there is no element there. So what we would do is we would simply return 0 from that point. Else if it is having some elements, then what we would do is return, this is how we find the index of it, return it minus T of ID dot begin. Okay, now we go down, that if it is not inside the range, that some part of it is there, I told you. So if some part of it is there, we would go down. Okay, so what we would do is int mid is equals to L plus R divided by 2. We would go on both sides, left as well as right subtree. So we would return query of ID multiplied by 2, and then this would be L to mid, and then LQ, and then RQ, and then the value would remain the same. And then the same thing would go for mid plus 1 to R, and then the right part would be ID multiplied by 2 plus 1, and this one would be mid plus 1 to the values r. And LQ and RQ and val would be the same. And we would simply add both of the values and we would return. Now the last part of it where I told that all the elements of A would be copied to the given V itself. So we would do this thing. First we would resize the T dot resize it to n multiplied by 4 plus 1. This is the common thing we do. Okay. And then we start iterating on the array and then we start inserting the elements. Okay. V dot push back A of I. Okay. We have successfully pulled it. Now we would build up. So I told you that the root node would be called as 1. And then we would build it from 0 till the value n minus 1. That is for the whole array itself. We would mention the range and then we would initialize a vector int of answer with the size as n. And then we would start doing the query. Okay. For int I is equals to 0. For int I is equals to 0, I is less than n and I plus plus. Okay. And then we would be having answer I is equals to query of 1, the root node. Then we would specify the range of LNR, okay, LNR, and then we would specify the LQ and the RQ, that is for the query. That would be I plus 1 till the very last. I told you that is n minus 1. And then we have the value, that is A of I. Now we would return the answer. So I seriously pray that I don't fall into errors. Okay, so we have some errors. So expected 64 1. So I think I did not give, yeah, I did not close this. It's done. Let us see how many errors are we making. Okay, we are getting a correct. What was the sample test case? Let us submit this. And yes, we got an AC. Now let us do the space and the time complexity analysis too. So for building up the structure, we are the height would be log n. Okay, remember this. So at each log n, we are having an array that is n log n multiplied by log n because we are doing a yes. That's it for today. Thank you and have a nice day. If you face any errors regarding this or you think or you have some confusions regarding the implementation or something, feel free to raise your doubts in the comment section. And let me know if you want a separate segmentary session on Geeks for Geeks channel. Thank you.